Safety. In this module, you will find out what safety stops are, understand their importance, and establish the best line of conduct for diving at different depths. Decompression in practice. It is possible to establish practical procedures to optimize decompression, increase the safety margin, and therefore make the dive safer. For example, you must understand when it is more useful to make a safety stop or if it is more convenient to ascend a few minutes before reaching the limit of the no-deco stop time. What is more, some modern theories regarding bubble formation and growth have brought to light the benefits of the deep stop, a procedure not considered in the traditional mathematical models. The safety stop. At the end of every dive, you must always make a safety stop of 3 minutes at a depth of 5 meters, 15 feet. This procedure, now in common use, began to be applied to recreational diving beginning in the 1980s. As long as you only make dives within the no-deco stop times, this stop is not strictly necessary from the point of view of decompression. However, there are practical reasons and benefits in preventing decompression sickness that make it advisable to carry out a safety stop. Making a stop at a shallow depth before surfacing gives you time to get your ideas in order, check the readings on your computer, and make sure that there is no boat traffic on the surface. It also gives you time to deploy a deco marker if necessary. From the point of view of decompression, this stop allows you to eliminate a little excess nitrogen, thus increasing your safety margin. The depth of 5 meters, 15 feet, was chosen because it is near enough to the surface that it can be seen and deep enough to reduce the risk of involuntary surfacing before the end of the safety stop. In all honesty, as we are dealing with a safety stop and not a compulsory decompression stop, the precision of the depth the stop is made is only relatively important. This is why dive computers allow the stop to be made between 3 and 6 meters, 10 to 20 feet. The ceiling. In order to better assess the efficiency of the safety stop, we must introduce the concept of a ceiling, which is generally only used for dives that exceed the no-deco time limits. In practice, it means that at any moment on the dive, there is a maximum depth to which you may ascend, so it is as if we have a ceiling above our heads. The depth of the ceiling varies because it depends on the depth you are at and how much time has elapsed. If you are at the limit of the no-deco time, your dive computer calculates that the permissible ceiling is 0 feet, meaning the surface itself. Instead, if you ascend later, the computer will indicate a ceiling at a deeper depth, for example at 2 meters, 7 feet, and you are obliged to make a decompression stop. Instead, what happens if you ascend before reaching the limit of the no-deco stop time? Your ceiling will be at a level higher than 0 meters, 0 feet, and therefore have a negative value. For example, you could have a ceiling of -3 meters, -10 feet, meaning that not only can you ascend to the surface, but you can also ascend another 3 meters of water, if there were any. This negative value is therefore a virtual ceiling, which helps you assess the safety margin. The higher the negative ceiling, the greater the safety margin. In practice, a dive with a ceiling of minus 1.5 meters, minus 5 feet, has a greater safety margin than one with a ceiling of minus 0.9 meters, minus 3 feet. The safety stop on deep dives. Let's see what happens on a dive to 40 meters, 130 feet, ascending 3 minutes before reaching the limit of the no-deco time. On surfacing, the ceiling is about minus 1.5 meters, minus 5 feet. Instead, now let's examine a dive made to 40 meters, 130 feet, to the limit of the no-deco time, when we add a safety stop of 3 minutes at 5 meters, 15 feet. On surfacing, the ceiling is about minus 2 meters, minus 7 feet. So making the safety stop is better than ascending before reaching the no-deco dive time. Always make a safety stop on deep dives. Dives at shallower depths. We have seen the benefits of the safety stop on a deep dive. Let's now look at a dive made to a depth of 20 meters, 66 feet. If you arrive at the limit of the no-deco time, the ceiling will once again be 0 meters, 0 feet. There is, however, a big difference from the deep dive. The ceiling remains negative for most of the dive, in practice until after the 40th minute. Considering that the ceiling rises on ascent due to the elimination of excess nitrogen in the compartments, you could even begin ascending 5 minutes before reaching the no-deco stop limit, so on surfacing the ceiling would be about minus 1 meters, minus 3.3 feet, giving a discrete safety margin. Now let's add a safety stop of 3 minutes at 5 meters, 15 feet, to this dive. We discover that the margin offered by the safety stop is, in terms of the ceiling, much less than minus 1 meter, minus 3.3 feet. Therefore, the protective effect of the safety stop for this dive is very limited. In effect, to have the same safety margin as you had beginning the ascent 5 minutes before reaching the limit of the no-deco time, you must extend the duration of the stop at 5 meters, 15 feet, to 17 minutes. So on shallower dives, it is certainly more beneficial to begin the ascent before reaching the limit of the no-deco time. Instead, if you reach the limit of the no-deco time, it is best to make a longer safety stop than the usual 3 minutes. What causes this big difference in the effectiveness of the safety stop on dives at different depths? As we have already seen, depending on the depth that is reached and the time spent there, some compartments reach the limit, while others do not. In particular, the deeper you go, the more the fast compartments move towards their limits, reducing the no-deco times. At shallower depths, the fast compartments are not affected, and it will therefore be the slow ones that establish the no-deco dive time. In short, the fast compartments control deep dives, while the slow compartments control the shallower dives. The elimination of nitrogen is calculated in the mathematical model that is based on half saturation times. In virtue of this, it is easy to understand that in the 3 minutes of the safety stop, more gas is released in the fast compartments than the slow ones. For example, a compartment with a half saturation time of 2 minutes loses 64.6% of its excess nitrogen, while one with a half saturation time of 640 minutes loses just 0.3% of its excess nitrogen. The safety stop is extremely important on deep dives, while it has little effect on the shallower dives. The safety stop in practice. Let's sum up the general rules for making a safety stop. At the end of every dive before surfacing, you must make a safety stop of 3 minutes at 5 meters, 15 feet. The safety stop is essential on deep dives. The safety stop assumes even more importance the nearer the elapsed time is to the limit of the no-deco time. On shallower dives, you should begin the ascent a few minutes before reaching the limit of the no-deco dive time. If you reach the limit of the no-deco dive time, the longer you have stayed at depth, the longer the safety stop should be. Deep stops. Deep stops are an interruption to the ascent at a determined depth. These stops should not be confused with compulsory decompression stops in that they are precautionary rather than obligatory. In practice, it is as if you were making extra preventive safety stops during the ascent. It was the ichthyologist Richard Pyle who, while making deep dives, noticed that he felt less tired after a dive when he collected fish samples than when he returned directly to the surface without collecting anything. He also noticed that these symptoms had more to do with gas absorption than the actual physical exertion he did. Considering the only difference between dives were the stops he made to carry out certain procedures to protect the fish samples he had collected, he assessed that these stops were the reason he felt in better physical condition after a dive. Pyle got into the habit of adding deep stops of 2 minutes to those established by the tables. The result was that his symptoms of fatigue almost completely disappeared. Pyle set the stops at a depth equal to the average of the absolute pressure of the depth he had been to and that of the first decompression stop. He would then repeat the stops using the same criterion until he was at a determined distance from the depth of his first obligatory stop. You will use a simpler system. Make the stop at half your maximum depth. For dives to 20 meters, 66 feet or less, it is not necessary to make any deep stops, just the regular safety stop. For dives between 20 and 30 meters, 66 and 100 feet, it is best to make, as well as the safety stop, a deep stop of 2 minutes between 10 and 15 meters, 33 and 50 feet. You can also always make it at 15 meters, 50 feet. For dives between 30 and 40 meters, 100 and 130 feet, you should, apart from the safety stop, make a deep stop between 15 and 20 meters, 50 and 66 feet. Also, in this case, it can always be made at 20 meters, 66 feet. Many modern dive computers calculate deep stops and indicate them during the ascent. As these are safety stops, they are optional, but it is advisable to make them, following the indications of your computer. Free gas decompression models. No logical explanation for deep stops can be found in the classic decompression theories. Instead, they become completely logical in the light of free gas or bubble models. These new models not only consider dissolved gas, but also the gas that remains in a free phase in the form of microbubbles or gaseous nuclei. The pioneer of these studies was certainly Dr. David Yunt, who in the 1980s proposed his model of varying permeability, VPM, one of the most widely used models in technical diving today. The conclusions of this model oppose those of the classic theories. The ascent must be very slow, particularly when leaving the bottom, and eventual decompression stops must be made deep. It is therefore evident how the recommendations to ascend slowly and make deep stops are justified by this mathematical model. Let's look closer at the basic elements of these new models. As a starting point, they established that part of the inert gas, about 10%, is not dissolved in the body tissues, but is in a free phase, in the form of bubbles, mainly in the bloodstream. But in order for a bubble of gas to exist in a liquid, its internal pressure must be greater than the ambient pressure. Molecules of liquid are greatly attracted to each other, so much so that on the surface this attractive force, surface tension, causes the molecules to form a membrane strong enough even for small insects to walk on. This surface tension tends to squash the bubble, so in order for a bubble to exist, it must have a pressure greater than the ambient pressure. The difference in bubble and ambient pressure is, according to Laplace's law, directly proportional to the surface tension and inversely proportional to the radius of the bubble, meaning that the smaller the bubble, the greater the pressure difference. However, if there is a pressure difference, the gas inside the bubble dissolves into the liquid. Consequently, the bubble becomes smaller, and the difference in pressure rises again, so the gas continues to dissolve into liquid until the bubble disappears. So all bubbles are destined to disappear after a few seconds. However, bubbles are found in fizzy drinks, where they stay for a long time. This contradiction led Yunt to study the persistence of bubbles, and he discovered that bubbles resisted for physical and structural reasons. Physically, bubbles tend to reduce the squashing effect of the surface tension by attaching themselves to the walls of a container, glass or blood capillary, whatever, or joining together. Structurally, every bubble is surrounded by a membrane created by surface activity, also known as surfactant. These surfactant molecules, thanks to a reciprocal action of attraction and repulsion, act like an elastic net on the surface of the bubble. The smaller the bubble, the more the net closes and obstructs the passage of gas from the bubble to the liquid, and vice versa. The ease of passage of the gas molecules is defined as the permeability of the bubble. If the size of the bubble increases, the permeability increases and vice versa. The name varying permeability model derives from this fact. On ascent, the bubbles of nitrogen are in a particular situation. They have a greater pressure in respect to the ambient pressure, but the liquid is oversaturated. If the pressure of nitrogen in the bubbles remains greater than the tissue tension of nitrogen, Pt, the gas tends to pass from the bubble to the liquid and decompression is optimal. But if a diver ascends too much, the volume of the bubble increases, according to Boyle's law. The pressure difference with the outside decreases, and the pressure of nitrogen inside the bubble falls below that of the tissue tension of nitrogen, Pt. Gas, therefore, passes from the liquid to the bubble, which increases in size, reducing the pressure difference with the outside, and so continues to grow until it becomes a substantially sized bubble and thus a potential cause of embolism. The aim of correct decompression is to find the right equilibrium between all these opposing factors. You must ascend to open the elastic net of the bubble and permit gas to pass, and also to allow the elimination of excess nitrogen. But at the same time, you must not ascend too much so as to keep the bubbles small and prevent the flow of gas between the bubble and the liquid reversing. The aim of deep stops is to give nitrogen in its free phase time to dissolve into the tissues, meaning to pass from a bubble to a liquid. In the VPM model and its derivatives, such as RGBM, it is possible to mathematically calculate the maximum acceptable level of oversaturation instead of using practical experimental tests. However, this results in very long decompression times, and the decompression profiles of the traditional models should cause explosions of bubbles. This is why the new models have been adjusted experimentally, as you can discover by attending the PSS Accelerated Decompression course. In the next module, you will find out why it is better to make deep dives from a boat, what to do if you become separated from your buddy, learn more about the concepts of trim and buoyancy, see how you should behave before and after a deep dive, and discover more about a dive computer. See you soon.